In this video, we discussed the autocorrelation of random process. Notation is R. R means autocorrelation. X, subscript X, is the random process xt. Autocorrelation has two times, T1 and T2. What is this? This is the expectation of two random variables take product, xt1 and xt2. And xt1 is a random variable at t1, and xt2 is a random variable at time t2. If we know the joint PDF function of these two random variables, these two joint PDF, we can take this product, this two random variable x1 multiplied by x2, and multiply by this joint PDF. We do the double integral, and then we can obtain this expectation. And we can see after we calculate this expectation is a function of T1 and T2, because there will be T1 involved here, there will be T2 involved here, because the PDF function is a function of T1 and T2. The autocorrelation can be obtained by evaluating this double integral. We can also have other ways to obtain this autocorrelation by directly taking the expectation of xt1 multiplied by xt2. We're using example to illustrate the calculation. Let's look at this random process. S equals a cosine 2 pi f naught t plus theta. Theta is uniformly distributed from 0 to 2 pi. So we can see this signal is a random process because there's a random variable involved or t involved. So what is autocorrelation? Rx t1 t2 as expectation of xt1 multiplied by xt2. So t1 and t2 is given. Those are two arbitrary times given beforehand. So xt1 we plug in for t equals to t1. And xt2 we plug in t with xt2. And then we take product. I take a squared out, and cosine multiplied by cosine. We're using this formula in triple identity. Product of cosine we can be written by summation of two cosine divided by half. The angle take the difference. The angle take summation. Expectation still here. And normally expectation we use square bracket here. So there's a square bracket here. There's a half here using the triple identity. Cosine, this angle take the difference. That's cosine 2 pi f naught t1 minus t2. And then the angle take the summation. Take the summation, there will be t1 plus t2, 2 pi f naught, and plus 2 theta. If we do expectations, expectation is linear. We can take in for different terms. So expectation of this term, and expectation of second term here, and a squared half is carried out here. If we look at this term, cosine 2 pi f naught t1 and t2, there's no random variables here involved. T1 and T2 are given, f naught is given, and here is constant. So therefore, we're using this property here, expectation of constant C equals to C. So therefore, this term, expectation, that equals to cosine, this term. Let's look at this term. If we look at this term, T1 and T2 are constant because it's given. And theta, that's a random variable. This whole thing cosine 2 pi f naught t1 plus t2 plus theta, that's a function of theta. So this is a function of theta. And so we really take expectation of a g theta. And we know this, if I take a function of random variable x, that equals to, we take this function multiplied by the PDF function of x, we do integral from minus infinity to infinity. And this is exactly what we did when we found the mean of this random process. For the PDF of theta, you only have non-zero values from 0 to 2 pi. The value is 1 over 2 pi, and beyond that, here is 0. That's 0. So this is f theta. And now we take this function here. We multiply by this PDF. We do the integral from 0 to 2 pi. To evaluate this integral, I have it here with a detailed step. Let me go through that. So a squared half is still here, integral here. And so I just copy this term down here. The integral is with respect to theta. And this we know this cosine a plus bx. If I take the integral of bx, that equals to sine 1 over b for sure. A plus bx. Right, that equals to that. Because if we take derivative of this, I'm going to obtain this integrand here. So that's the way to check if we got the integral correct or not. This whole thing is A. And B here, that's B. And theta, that's Ex. Okay, so we plugged it in, that's half here, and that's sine. The definite integral, theta equals 0 and 2 pi, we plug it in, so this term equals 0. In other words, this integral is 0. We can obtain the autocorrelation for this random process here that equals to this term. The results of the autocorrelation is summarized here. It is a function of T1 and minus T2. That's the difference of T1 and T2. Let's define a special category of random process called wide sense stationary process, and shorthanded WSS. And when people talk about wide sense stationary random process, people normally call it a stationary process for short. And when we talk about stationary process, we know that's the wide sense stationary. It follows the definition of two conditions. One, the mean of this random process is not a function of t, it's independent of t. And second, the autocorrelation only depends on T1 minus T2. We call it tau. Let's look at this random process. We know the mean of this random process. We do this. This is a function of theta, and this is a PDF of theta. And we do the integral from 0 to 2 pi, and that equals 0. And we know the mean does not depending on t. And the autocorrelation we just derived is a function of T1 minus T2. So that's tau. So in this case, this random process, it is a stationary process. Because of these two properties that stationary process has, it makes the process more trackable. And normally for stationary process, the autocorrelation can be reached in this way, Rx, t plus tau, and t. So this quantity is T1, and this quantity is as a row of T2. It is the expectation of x at time t plus tau multiply the random variable at t, and we do expectation. If the random process is stationary, it is a function of, let's say g, a function of t plus tau minus t, that equals g of tau. Because for stationary process, the autocorrelation depends on the difference of this time t1 minus t2. So this is t1, this is t2. So we take the difference, that is tau. That is tau here.